Welcome back everyone, and in this video we are going to talk about unsupervised learning. To be honest, we will talk about unsupervised learning in only with respect to two very popular methods of this area. There is much more, but I just want to give you a short introduction and an idea what you can think about when you hear about unsupervised learning. And I think the two things we're discussing here are already very good and handy examples which you can use for many different applications. So I hope that it's going to be helpful as well for you. And also I think it's very well suited to introduce you to the idea of the methods for clustering and dimensionality reduction. So very generally speaking, the big difference between supervised learning and unsupervised learning is if there is a target variable or if there is not a target variable. Okay, so for the prediction models that we discussed so far, what we really did was to have a conditional perspective on a variable of interest that needs to be defined by us and sometimes also needs to be labeled by us. So the conditional perspective was always, if there is some information given by feature variables, then with this conditional on this information, what do we think about the target variable? And what do we think about is an easy way of saying something like, what's the expected value for the target variable? That is basically the question we're trying to answer when we are building regression type models. Or what's like the conditional probability of the target variable for belonging to category K. Yeah, that's what we did when we were talking about the classification methods. And what we are now interested in when we're looking at unsupervised learning is simply the distribution of all the variables that are of interest to us. So for instance, all the feature variables, but doesn't necessarily have to be only feature variables, could also include the target variables. But now we are going to an unconditional perspective and are trying to take a look and find out about the general relationships and behavior among all the variables without really conditioning on a certain subset of the variables and taking a look at a specific variable. We more or less now are interested in the overall multivariate distribution of the variables in our data set. And very popular tasks that belong to the category of unsupervised learning is, for instance, clustering. And I think this is something very intuitive that you already have an idea about what is meant by clustering. So we have a big amount of data samples. For instance, the data sample could be customers, as you will treat them in an example that will come up in this or in the next video. And we want to make subgroups of the customers, and we want not to group them randomly. We want to group them in a way such that the data is more structured. Typically that means that the customers within a certain segment, within a certain cluster, are more similar to each other than they are to the customers of the other clusters. So clustering is some way of bringing structure in the data and cleaning up the data a little bit such that you will have that you can work more easily with subsamples of the overall data set. Dimensionality reduction is something which is, I would say, not so intuitive because you do typically not have any experience with that in your regular life. But it is a very, very important topic for all the methods that belong to the area of data science. Dimensionality reduction, as the name suggests, is simply the wish to reduce the information that is given in many dimensions, and by many dimensions typically we mean that is given by many feature variables. And in order to to reduce the information that is given in many dimensions into a smaller amount of dimensions. And that has many reasons why that is so helpful in some cases and also necessary in some cases. The first and most easy one that you can think about is, for instance, visualization of the data. We as human beings are only able to visualize data in at least 2 or 3 dimensions. Once we have more than 3 dimensions, it is not possible for us to visualize data. But sometimes, of course, we may have data with like 5 or 10 dimensions, meaning we have collected information for each sample with 10 feature variables. And the only way to visualize this information is that we need first to condense the information that's given in the 10 feature variables into a dimensionality that is, that we are able to visualize, and that is to, reduce the information given in all the feature variables into 2 or 3 fictional variables, but those variables should contain as much as information as possible and as much of the original relationship between the feature variables as possible in those 2 or 3 fictional variables. But it's not only visualization, also the so-called curse of dimensionality is an important reason why dimensionality reduction is so important when, for instance, we want to succeed also in prediction tasks. Just in a short way, the problem is the more dimensions we have, so the more feature variables we have, the more likely they are to be far away in a high dimensional space. And when you think about the supervised learning tasks, what we basically do is we try to identify, similar observations that are similar with respect to some feature attributes. And then for these similar observations, we hope that also the prediction for the target of interest or for the target is similar. And if we have high dimensionality, meaning if we have a high amount of feature variables, then the problem is we are very likely not to find many observations that are similar to each other, simply because of the fact that if we have high dimensions, there is a great likelihood of those samples to be far away from each other in the high dimensional space. I know that this sounds really fancy and kind of out of space, but bottom line here is it is often very helpful first to reduce the dimensionality in your data set and then use those reduced dimensions and those variables in order to build up a supervised learning model that we discussed so far in the course, okay? But we'll come to a popular method of dimensionality reduction in the next videos. In this video, I want to share the knowledge with you for a single clustering algorithm, which is, in my understanding, one of the most popular algorithms. And there are many more algorithms, but we want to discuss only this one to provide you an idea how clustering works and what's unsupervised learning in this context, and then you're good to go to learn about other methods on your own. Okay, the algorithm we are discussing now is the k-means clustering algorithm. And I would say it's, you will, as always, as you're already used to it, there is a certain formalism in my slides here, because I think that's important to, provide also an accurate notation of the methods. But the idea of k-means clustering is, I think, very intuitive and easy to understand as soon as you understand the concept of similarity among vectors. Okay, I hope that you're already familiar with that from school, to be honest, or I think that at least also in school you're already discussing what a vector is, and already maybe you are, let me just go directly to this visualization. In school, I hope that you already have seen things like that. So you have here a vector like that could be starting from the origin, could be visualized by that point, like going from here to there, that could be this vector. And behind this vector is here, in that case, a two-dimensional vector, which has this is just defined by two numbers. So the number of x1 and the number of x2 here. And the same thing holds true for these other observations here. And if you understand the concept of similarity between vectors, then I would say basically that's more or less everything you need to understand when it comes to the k-means clustering algorithm. But let's just go to the start but go to an example. And I mean, this is like a fictional example as always, so the actual realizations doesn't mean anything here. But assume now that we have only two feature variables in our data set for each sample of the data set. Okay, and here we have just fictionally three samples in our data set. So this is the first one, whose realization of the first feature is 0.5, and whose realization of the second feature variable is 2. Then we have here the second observation in our data set, and here we have the third sample in our data set. And now we are not only interested in a single variable, so there is no target variable or something like that. We are always interested in all the variables. So here are the 2 variables and its realizations for each sample. And what is an important concept that is needed when we want to understand the k-means clustering algorithm is to understand that we need, or that we want to quantify which of those samples here, so which of those rows is more closer to the other rows and vice versa, or at least on a pairwise point of view. We need to be able to understand and to quantify by a single number if, for instance, this first observation is closer to the second one or to the third one. And one way of measuring this is the Euclidean distance, or also what's used by k-means clustering is the squared Euclidean distance. And even though that looks complex, we have here n feature variables for each sample in our data set. And when we want to quantify how close the observation I in our data set is to the observation L in our data set, we simply calculate the squared deviation of each feature variable, or if each realization of the feature variable for the sample. So here, for instance, we calculate 0.5 minus 1 if you want to count the, or if you want to determine the difference of the first feature variable and the first and the second sample in our data set, and then we square those values as always, and we do the same thing here but also for the second feature variable. So in order to determine how similar the first observation here, so the first sample, is to the second sample, is simply that we calculate those differences here and square them up and sum them up. Okay, and that is what this means here. And we can do this for all those observations. And if we do this for this simplified example here, then we have a single number that tells us that observations 1 and 2 are kind of close to each other, that observation 1 and 3 and 2 and 3 are like more far away to each other. That means the observation 3 is likely to be far away from 1 and 2 than 1 is in comparison to 2. Okay, and this is also what we can observe here in this case, because we have only 2 dimensions, we have only 2 feature variables, and here we can see the observation 1 has 0.5 and 2, so that is where we are here. This is then the second observation, and this is the third observation. And we can see also visually what's quantified by the Euclidean or by the squared Euclidean distance. Okay, so we are able to quantify how similar an individual sample in our dataset is to the remaining samples on a pairwise relationship. And that's like the most important principle that you need to understand right now when it comes to understanding how the k-means clustering algorithm works. Okay, so if you do not understand this so far, go back, watch the last 5 minutes again, or maybe search for another source which explain this maybe more eloquently and better than I do. But that's important to understand what follows now. Okay, so because what the k-means clustering algorithm does is, if we have a certain amount of data points in our data set, so a certain amount of samples, so in that case it would be 3, but obviously in reality it would be more samples, then what it does, it starts with a number of clusters that we define as a user. So assume for the moment we want to cluster those 3 data points into 2 clusters. Then what the algorithm is supposed to is to find clusters with what is called the let me just go there to with centroids. So each picture that as a representative of the cluster. So for instance, like we could think about here, and we see it here, it would be obviously quite reasonable to use a cluster for those 2 points and to use a cluster for this individual point. So the centroid of the first cluster here could be pictured by yourself by its representative, and usually a representative here is given by what we would do as the average observation of those two observations. And average observations simply would mean that we, calculate the average of 0.5 and 1, so 0.75, and here the average of those two values would be 1.5. Okay, so if we go here, then we would end up at this point here. So for a first cluster here, then we would have a centroid, which is here. And okay, obviously for the second cluster, the centroid is the point by itself. Okay, and then what the clustering algorithm does is for each cluster, it looks like it goes to that point, and now it searches for the centroid with the least distance. So if we would have a centroid that is here and we have a centroid that is here, then obviously that point would be asserted to that cluster with that centroid here. The same holds true for that point with that centroid here. And then it calculates the similarity, so here the squared Euclidean distance of that point to its cluster centroid and of that point to its cluster centroid. And it also counts the squared Euclidean distance from that point to its cluster centroid. In this case, there will be a special case because the point itself is its cluster centroid, so the Euclidean distance is 0. And in the end, it sums up over all the distances of each point to its cluster centroid. And each point is asserted to the cluster centroid with the least distance. And that is again like some kind of a minimization problem that could be handled by the choice of how many, given a certain amount of clusters, then we need to define the cluster centroids for each cluster, and we need to assert each point to its cluster. And if we do this and calculate then the sum of the distances of all the points to their cluster centroids, this is what we want to minimize in order to have the best cluster segmentation that we may have for a given number of clusters. Okay. Definitely, this is going to be much more easy if we take a look at an example right now. But for the moment, let me just also add this note here, what I already discussed so far. Also formally, usually we never need to care about finding the optimal centroid. So meaning for a certain cluster K, which value should we choose as the representative, because typically the average vector of the vectors within a cluster is what minimizes the squared deviations of all the points to the cluster centroid for a given cluster. Okay, but let us take a look at an example how this would actually work in reality. So assume now again, as we further can visualize it, we have more observations now, but still we remain with two feature variables. So here x1 and x2. What the clustering algorithm does in order to solve its minimization problem is it starts in the beginning with some random centroids. Okay, so we're in the beginning, we're just guessing what could be a reasonable centroid. Okay, so then that's represented by those four colored markers here. And now for each point here, it calculates the distance, so the squared Euclidean similarity, to each centroid. So for that point here, it calculates it to that green marker here, to the purple one, to the blue one, and to the orange one. And then it asserts this point to the cluster with the lowest squared Euclidean distance to the marker. So obviously that would be the green one here. Okay, so more or less all those points are asserted to the green here. Then especially those in this area are asserted to the cluster with the purple centroid, and the blue one and the orange one are the same. So if we do it like this here, then it would look like this. Okay. Now in order to further improve the clustering and the assertion of the points to the cluster centroids, this is done iteratively now for many steps. And we always have two steps. We always have the step of first finding the cluster centroids that are the representatives for each cluster, and then asserting all observations to the cluster centroid which is the closest to them in here the two-dimensional space. And now we are going to start again. So we are looking for those green points for the best representative. And obviously it's not that marker here outside. The best representative meaning the centroid such that on average the similarity to those green points is the highest. So it's likely to be somewhere here. Then for the purple points, it's likely to going somewhere here in the center. For the blue ones, it's likely going to be here. And for the orange one, it's likely going to be somewhere here. So like for all the green points, we calculate the average and use this as a new centroid for the cluster that for which the green points are made now. Okay, so that is what we do here. And now this changes. And now it really gets boring because now we're doing this more again and again and again. So again now, for all points, we're calculating the distances to the centroids and assert each point to the centroid with the lowest distance. Okay, that's what happens here. And then at some point, the cluster assertion doesn't change anymore, and then we stop. Obviously, as always, this is not something that you need to do manually. This is going to be done by the k-means submodule in the sklearn package. Okay, what's important to understand and to know here is, or some important knowledge here is, k-means clustering usually is made only for feature variables that are strictly numerical variables. So if you have categorical data or a mixed data set, meaning that you have a data set that includes numerical feature variables and categorical ones, usually you should use a different algorithm that is called k-mode or k-prototype. But for the moment, do not care about that too much. Just remember that usually and typically k-means is only made for numerical feature variables only. You will see some people who want hot encode category data and still use the k-means clustering, but in my opinion that's not 100% correct, and you rather go with the k-prototype algorithm that is also available for Python users. But for the moment, I hope you understand the basic principle here. So the task of finding clusters here is maybe divided into two subtasks. First of all, you need to find good representative values for a given cluster, and you need to assert all the points to their representatives that are the most similar to them. Okay, and similarity usually here is calculated as the squared Euclidean distance. There are other metrics that can be chosen, for instance cosine similarity, but in the original algorithm, as far as I'm aware of it, using the squared Euclidean distance. So, and what's behind here is to find an ordering in the data, so to find a cluster segmentation which reduces the sum of Euclidean squared distances of all the points to their cluster centroids, so to their representatives. I hope that this is at least a little bit clear, or the idea is a little bit clear, okay? And this is what how k-means clustering work. Obviously, as we as users define the amount of clusters that's going to be estimated when we are estimating it with the algorithm, the question remains is how many clusters should we use? And I mean, there is no 100% clear method here, but what's usually what I would always do are both things. First of all, you can choose the so-called elbow method. It's not visualized on the slides here, but we will see later in the example how it works. Basically, once we are finished here with the estimation of the clusters and the cluster centers, what's calculated is what is called the inertia. And the inertia is simply the sum of all the distances for each point to their cluster centroids. Because if we have a good cluster segmentation, obviously the sum of like the differences for the individual points to their own cluster centers, they should be hopefully very close, so they should be very similar. And for a different amount of clusters, we always can calculate the sum of the distances from each point to their cluster centroids. And then we will, find we can see how this progresses for an increasing number of clusters. And then we will choose according to the elbow method, which I will explain in the next video when we take a look at a real data set. Furthermore, what we also can do, you can calculate what is called the silhouette score. The silhouette score is usually normalized in the value range between -1 and 1. And what it does is it compares the dissimilarity. So again, how big the squared differences is according to the Euclidean distance if you use the Euclidean distance. So what it basically does, even though again here it looks complex if we write it down formally, it just uses the average dissimilarity from a observation, like from a single observation I. It counts the dissimilarities to all the observations in its own cluster. Okay, so here, for instance, if we do that for the green point here, then we would count the dissimilarity from that point to that point, to that point, to that point, so to all the green points. By dissimilarity, I always mean here now the squared Euclidean distance, and we average it, okay? And that is what is formally described here. So the dissimilarity, the average dissimilarity of a point to its own cluster, neighbors. And then we do the same thing, okay? Also, again, calculating the average dissimilarity of that single observation, but now to the other clusters, okay? So go to that green point here. What we first do is now we calculate the similarity to all the purple points and average it. And remember that number. Then we calculate the dissimilarity from the green point here to all the blue points, average it, and remember this number. And we do the same things with the orange point and average it and remember this number. And then for the purpose of comparison, we compare the average dissimilarity of that green point to its own neighbors with the average similarity to the cluster that is the closest. Okay, so here it likely would be the purple ones. And then that's what's calculated here. And then what we do is when we calculate the silhouette score for this observation, we take a look at the average dissimilarity to the observations in the cluster that is the closest to its own cluster. And here we have some, we have the average dissimilarity to its own neighbors in its own cluster. That's just here to normalize it to the value range between -1 and 1. And as you can see here, usually if clustering for that point works well, then obviously we would expect that this value is higher than this value because this is the dissimilarity to points from another cluster, and this is the average dissimilarity to the points of its own cluster. So we would expect that this would be a positive number. As long as this is a positive number, then the segmentation seems to behave as expected because the similarity to its own neighbors is higher than to the points of the next cluster. But in theory, or like in reality, it's also possible that this gets negative, which just means that for that observation, even the points of the next cluster are more similar than the neighbors from its own cluster. Okay, so a positive value speaks for a distinct separation, and a negative value is a bad thing because that means that this single observation would better fit into another cluster. In order to, we can calculate this for every observation in the data set, and in order to get a comprehensive overview, of course, we can calculate the average silhouette scores for all the observations here, okay? And then what I would recommend to you is to take a look at the silhouette figures that I really like here. So what you can see here, for instance, for our example with the 500 data points is in an increasing fashion, like every vertical line here represents a single observation and its corresponding silhouette score. So here, for instance, if we would use 2 clusters, then approximately the first 150 observations belong to the first cluster. And this is in an increasing fashion the silhouette scores for the observations in that cluster. So we can see that for the first cluster, the silhouette scores are probably on average like 0.7 or something like that. And then we can see here again from the worst to the best distinction for the observations in the second cluster. And you can do that obviously for different amounts of clusters. And yeah, as you can see here, like 3, like if you take a look at the title here, so for 2, for 3, and for 4 clusters, Obviously 2 is not a good idea, but then we could, according to the average silhouette score, we would use 3 clusters, but then we can see here that this leads also to observations which are not very good segmented within the first cluster. So averaging is always something which, you know, reduces information, and here we can see that if we would use 4 clusters, it's better balanced within each cluster. So we would use 4 clusters in our example, which you can see visually is obviously the best idea here. Okay, so that is what you can take a look at if you want to, you know, get a feeling for the best, hopefully best amount of clusters you're going to use. All right, so that is basically what you need to understand about k-means clustering, or at least it's always a short introduction into the idea of clustering. As always, if you're Googling sklearn clustering, then you will find a very good documentation of all the base clustering algorithms that are implemented in the sklearn package, and you will find the k-means clustering here in its explanation. And if you go on that, you will find the submodule and how it's defined, that you define here, for instance, the number of clusters, and that it will give you something like the inertia, so the sum of square distances of samples to their closest cluster center weighted by the sample weights if provided, and so on and so on. So as always, yeah, very useful and, you know, defined in a very similar way. So you should already be used to how you are handling and working with those functions. Okay, so in the next video we're going to take a look how we what we can do with k-means clustering and how we will use it when we will work with real data and Python code. So yeah, I hope you're excited about that, and see you in the next video. Bye bye.